Alright, so in this podcast we're basically looking at wave equations and kind of doing the only math we really have this unit. And wave equations, there's two of them. You need to be familiar with both, and they can play into each other. So our first equation is this: C equals lambda nu, and our other equation is E equals h nu. And in both of these equations we have a constant. So in this equation our constant is c, and it's the speed of light. And because light is one form of electromagnetic radiation, actually every form moves at the same speed, and that is 3.0 times 10 to the 8th meters per second. Right? So constant, it's always that. Just be able to recognize it, and I will give that number to you. Over here, our constant is the h, and it's known as Planck's constant. And Planck's constant is 6.63 times 10 to the negative 34th joule seconds. So just joules times seconds. And again, that's a number. I'll give it to you. You just need to know how to use it. Alright? So here's what a question could look like. What is the frequency and frequency, its symbol is nu, so I put nu. What is the frequency of light with a wavelength? And then wavelength is this funky lambda thing. What is the frequency of light with a wavelength of, let's say 340 nanometers? So another thing you need to be familiar with is nanometers, and we'll see this pretty often because it's what visible light is measured in. Alright, so 1 meter equals 10 to the 9th nanometers. And again, nano, you possibly have heard of nanotechnology, kind of building really, really small machines. They're machines that are the size of atoms are typically 10 to the negative 10th. So angstrom is the measurement for that. So it's a little bit bigger than the size of atoms really are, but it's really, really, really small. So these wavelengths are crazy small. But anyways, what's the frequency of light with a wavelength of 340 nanometers? So we know frequency, and both these equations have frequency in them. So we really need to look at what's the other bit of information we have, and we know wavelength in this case, because wavelength again is this lambda upside down y. So for our first equation, we're going to use the equation on the left because we know wavelength and we're solving for frequency. If we knew energy, we would be using the equation on the right. So it's simply our constant, which is 3 times 10 to the 8th meters per second, equals wavelength, alright, which we know. And for this, we're really going to do 340 nanometers. We're going to do a little fence and rail here in our parentheses. And we have 10 to the 9th nanometers equal 1 meter. And we're going to multiply that by x. What we're going to find out is if we take 340 and divide it by 10 to the 9th, this really becomes 3.14 times 10 to the negative 7th meters. Alright? So in order to solve this, we're going to really divide both sides by that same constant we just found. So we're going to divide both sides by 3.4 times 10 to the negative 7th. We're going to find out that our frequency is 8.82 times 10 to the 14th. And then our unit for frequency is always hertz. And a hertz is the same as a 1 over seconds. Alright? So notice over here we basically have meters per second. We're dividing it by meters, so what we're left is just per second. Alright? So the next thing we might do is we can just follow up this question with what is its energy? And by its, we mean a photon of light. So a single photon. What is its energy? Alright, so again, now we're going to use the equation on the right. we already know frequency because we just solved for it. So we really have E equals h nu, and nu is frequency, which we just found out. So really we have x equals 6.63 times 10 to the negative 34th. And remember, this unit is joules times seconds. We're going to multiply that by 8.82 times 10 to the 14th. And it's hertz or per seconds. So if you multiply joules seconds over per seconds, our seconds are going to cancel and we'll be left with joules, which makes sense because that is how we measure energy. Alright? So I'm going to put a J over here. When we do that math, we get 5.85 times 10 to the negative 19th joules. Alright? So it's a crazy small amount of energy, but that's for one single photon of light, or really for something the size of an electron. So we never find an electron by itself. We find Avogadro's number for electrons. So if we take that number and multiply it by 10 to the 23rd, we have thousands of joules. Alright? So again, two equations. Here's just two simple examples. They're really easy equations to use. We'll be given one thing, there's a constant, we're solving for the other thing. Alright? But you can kind of see how they're used together in both these examples.